In this video, we're going to be talking about L'Hopital's rule, which, as you can see written here, is used for indeterminate forms that are quotients. So let's just talk about that for a second. There are a lot of indeterminate forms. The most common is 0 over 0. Is this a quotient? Yes, it is. Quotient meaning division, basically, right? Something divided by something else. Or, for example, infinity over infinity. That's indeterminate. It's a quotient. Or really any combination of infinities, like negative infinity over infinity, etc. Right? Like a positive negative infinity over positive negative infinity, all that's fine. But there are some indeterminate forms, like for example 0 times infinity. That is indeterminate form, but it is not a quotient. Right? Infinity minus infinity. That is indeterminate form, but is not a quotient. Okay, so first things first, this is for limits only. And when you get an indeterminate form, some indeterminate forms means you can use L'Hopital's rule. So what's the gist of L'Hopital's rule? The main idea says that if you are taking a limit of something that's a quotient like this, and you get something indeterminate, like 0 over 0 or infinity over infinity, instead you can take the derivative of the top and the derivative of the bottom and evaluate that limit instead. And I'm not going to give you a sort of formal statement of this result. You can find it in a textbook or online somewhere, but this is the gist. And the reason this works is when you have something that's like infinity over infinity or in 0 over 0, it's really like a race between the functions, like which one is going to 0 faster than the other. Because as you're sort of, as these things approach 0, remember they're not true zeros because that's the nature of limits, right? We're just sort of getting close to this, as close as we want, but we're never actually going to hit it. So it's a matter of which one of these is approaching 0 faster, which one of these is approaching infinity faster. So because it's about sort of how the functions are changing and it's about their sort of growth rates, it kind of makes intuitive sense that instead of comparing the originals, you can just compare how they're growing. Because remember, the first derivative models rate of change for a function. So let's just do a couple examples and see this in action. So for example, let's evaluate the limit as x approaches 2 of x cubed minus 8 over x minus 2. So first you can check this, and when you do, you get 8 over 8 minus 2 over 2, or 0 over 0. Okay, so that means this is an indeterminate quotient. We can use L'Hopital's rule. Now, if you didn't have L'Hopital's rule, you'd have to know how to factor a difference of cubes, and then you could do it by factoring. But a lot of students don't really like difference of cubes, or they don't like factoring cubic things. So instead what we can do, I'm just going to indicate L apostrophe to mean I'm using L'Hopital's rule, is instead of evaluating the original limit, I can take the derivative of this. Now remember, this is just the derivative of the top and just the derivative of the bottom. We are not doing quotient rule. Okay, so there's no quotient rule involved with L'Hopital's, even though you are dealing with quotients. We're not taking the derivative of all of this. We're just trying to compare how fast is this growing, how fast is this growing. So I take the derivative of the top, I get 3x squared, that 8 disappears. I take the derivative of the bottom, I get 1. And then if I evaluate this limit, right, I just plug in and see what I get. 3 times 2 squared over 1 looks like 12. And it turns out that's what the limit is. Okay, so this is sort of a simple version of L'Hopital's rule. I had something, I checked the limit, I got something indeterminate, specifically an indeterminate quotient, so instead I just take the derivative of the top and bottom and I evaluate that limit instead. So this is really powerful. You don't have to use a lot of fancy machinery. This is sort of like a tool that works well in a lot of situations. Let's try one that's not quite as straightforward. So now I'm taking the limit as x approaches 0 from the right of x times the natural log of x. So if you check this and plug in, you'll get 0 when you plug in 0 here. And as x approaches 0 from the right, natural log of x is going to negative infinity. Okay, so this is 0 times negative infinity. That is indeterminate form, but it's not a quotient. So that means you can't use L'Hopital's rule yet. Okay, so there's a way around this, which is whenever you have an indeterminate form that's not a quotient, you just turn it into a quotient. And there's a couple of ways you can think about doing this. For example, if you had infinity minus infinity as your indeterminate form, you can usually combine those expressions into a single fraction. But when you have a multiplying indeterminate form like this, 0 times positive or negative infinity, really what you want to do is force one of them into your denominator. Okay, so what we're going to do is not take any derivatives, but instead just sort of use some algebra to rewrite this. So instead of x times natural log of x, instead what I can do is think about this as being natural log of x over, and then you might want to ask yourself, what can I write in the denominator to make this expression original to this one? So pause for a second if you want to and think about what that would be. Okay, so a plain x in the main line is the same as an x to the negative first in the denominator, right? The cost of moving an x across the fraction bar is to switch the sign on the exponent. So this is really like an x to the first, and we're just making it a negative first when we move it down low. And now, if you sort of check this, remember this is sort of, this is 0 from the right, natural log of x, and then if you want to write it as a complex fraction, x to the negative 1 is like a 1 over x. And then if you checked this, you would see natural log of x is still going to approach negative infinity, and then 1 over x is going to be 1 over 0, which is the same as a sort of infinity. So now it's an indeterminate that is a quotient. So on this thing I can use L'Hopital's rule. So now I will use it. So according to L'Hopital's rule, I'm just using this L apostrophe to indicate that I'm using it. I'm going to take the same limit. Nothing about this limit changes. The derivative of natural log of x is 1 over x. The derivative of x to the negative first is negative x to the negative second. So now if I clean this up with a little bit of algebra, you can see that this will be 1 over x divided by negative 1 over x squared, and then instead of dividing by that 1 over x squared, I can just flip and multiply. So really this is like this, right? So instead of dividing by negative 1 over x squared, I can multiply by negative x squared over 1. Well, then I can see that one of those x's is going to cancel. So this is really the limit as x approaches 0 from the right of negative x, right? Because this x cancels out one of these x's. And then if I evaluate this limit, really this is just like negative 0 or 0. So L'Hopital's rule, if you don't have an indeterminate quotient right away, you can still use it. You just got to make it into an indeterminate quotient. Okay, one final thought here is if you use it wrong, it's not going to give you the right answer. That's maybe obvious, but it's worth pointing out. For example, you get something like this, and you're like, oh yeah, I should just use L'Hopital's rule. So let me get a different color here. So let's just say here, I'm like, oh, I know this is supposed to be L'Hopital's rule problem. That's what we've been doing. So I go ahead and just start doing this. Derivative of the top is 3. Derivative of the bottom is 1. Oh, 3 over 1, that should just be 3, right? No, that's not right. What did we do wrong? So you may want to ask yourself, again, pause and ask yourself what went wrong here. Okay, what went wrong is we didn't have an indeterminate quotient. In fact, we didn't have an indeterminate form at all, right? If you want to evaluate this limit, you just plug in. And I get 0 over 1, which is plain 0. No machinery required, right? So this is the correct answer. This, not so good. Okay, so do not make the mistake of thinking you can just use it all the time. Okay, you have to have an indeterminate quotient if you want to use L'Hopital's rule. And again, the main idea here is you're comparing growth rates. When you have an indeterminate quotient, it's really about how fast is the top approaching that 0 or infinity versus how fast is the bottom approaching the 0 or infinity. So instead of thinking about regular f over g, you can think about their rates of change, or in other words, their first derivatives. Also worth mentioning is, if you use L'Hopital's rule and get another indeterminate quotient, then just do it again and keep doing it until you don't get an indeterminate quotient. All right.